it's one. You'll talk about Fermion-Monopole scattering and standard model.
Hello, thank you for having me. My name is Rishi. You can tell I've come from London because I'm wearing shorts and sandals. This is essentially on the surface of the sun for me. This is great. Thomas told me this will be a relatively informal, this is a fairly informal meeting, and I want this to be informal, so please do ask me questions. I've got like 20 slides, so stop me. This is based on work, in the most part, this first paper came out in late 2023, but I will say some things about some more recent developments towards the end. So I want to tell you what the point of this talk is. Normally I like to tell people what the point of my talks are, and there's a few bullet points, and there's a few things that maybe you don't know that you will know by the end of it, and a few ideas. I like this talk because the entire point of this talk is this one equation. This is not my equation, I didn't write this down, Curtis Kahn wrote this down in 1984. And this is standard model physics. And what does this equation say? Kahn was interested in what happens when we throw fundamental particles in a standard model into a magnetic monopole. And what he says, what he computed, was that if I throw in a right-handed electron into a magnetic monopole, what comes out is half of an up quark, half of another up quark, half of another left-handed quark, and half left-handed left. This equation is complete nonsense. You can't have half integer or non-integer occupation numbers for fundamental particles. But nonetheless, there was a sense in which this equation was the right thing to write down. This half didn't come out of nowhere, it came from a calculation. The point of this talk is to understand, firstly, where does this half come from? And secondly, what is the correct version of this equation? What is the version of this equation which actually makes sense? That is what I'll hopefully explain by the end of the talk. So let me give you an outline now of what I'm going to talk about. First, I'm going to explain this very old problem, this 40-year-old problem. And the problem says that if I scatter low energy, consider low energy scattering of light fermions off heavy monopoles in a theory, so this is in a particular regime of energies, that I necessarily generate outgoing states which have fractional occupation. It's weird states, exotic states I need to understand. And now I present a new solution, a solution that is mathematically complete, a solution which we really understand, which is the statement that these outgoing excitations, these additional states that I need in my spectrum, can be understood as living at the edge of a topological surface. So this is very much in this kind of modern language of global symmetries, or generalized symmetries. Then I'll apply exactly these ideas to the original case of interest, the case that Callum was interested in, which is the standard model itself. And then I'll talk about some other directions, in particular some things that we still don't understand, of which there are quite a few, and some directions towards solving those remaining problems. So let me first talk about this problem. Let me motivate it. I should say that if you want to think about this talk from the kind of most esoteric standpoint, you could say I'm looking at the boundary conditions of massless fermions in the presence of a top line, and that could be it. But I want to actually motivate why I care about that. And so let's do that. I want to consider some generic non-abelian gauge theory with some Higgs theory. This theory has some topological, generically, not always, depending on the topology of the gauge group, but generically we'll have some topological solitons called top polycom monopoles. These are smooth solutions to the equations of motion. These are finite energy configurations. You have to include them in the path integral. They're not a choice, they are there. And I want to study scattering off these top polycom monopoles, but in a particular regime in which I have a useful and relatively simple effective field theory description. This is the scattering of massless fermions. So I really want to specify here, these are not fermions which are given a mass by this Higgsing. These are other fermions which remain massless far below this Higgs scale. I want to scatter them at energies much lower than this Higgs scale. This is a regime in which the monopoles themselves are very heavy. I can treat them as very heavy objects. This regime, I can, instead of thinking about this the non-abelian object and all its UV degrees of freedom living in it, I can model it as just a top line in my low energy effective description. So I pick out some point, say at the origin of space. I'm always in 3+1 dimensions here. And I excise a point and I thread some magnetic charge through there. So if I measure the magnetic flux through any two-sphere or any surface enclosing that point, I measure some integer n. I should say I'm making an assumption here, an assumption that goes into why this effective description is the relevant one, which is that there is an internal gap. So this non-abelian object, this topological monopole, has internal degrees of freedom, but they all there's no gapless modes generic. They have a gap. This gap is very, very small. It's suppressed by the Higgs scale, but nonetheless there is a gap. There are situations in which you do not have an internal gap. These are supersymmetric situations. If you have a supersymmetric situation, you'll have truly normalizable Fermi zero modes to correspond to internal degrees of freedom. I need to now dress my top line with some localized degrees of freedom to have a good IR expression.
That's why the gap was so. I sort of thought that the diode state was like a bound state with a W boson or something.
Yeah, so small, it depends on which units you're talking in, I guess. As a fraction in units of the monopole mass itself, then the gap is small, but
that's fine. Like the monopole mass is 1 over g squared.
Yeah.
I think it should be awarded that the W of boson mass, roughly speaking, in that Higgs theory.
yes. Yeah, that's consistent.
Yeah. So it's still in a gut, it would be like the gut scale.
Yeah.
So it's huge.
Yeah, well,
From the point of view of the standard model.
exactly. Yeah. So yeah, I'm using Higgs scale and gut scale. I'll say that later. Here I'm in a very generic situation, but yeah, when I say Higgs scale, I mean the gut scale. So let me talk about a very generic setup. I'll specialize to the standard model a bit later. I want to think about abelian gauge theory in 2 + 1 dimensions. I want to have a top line of charge. In kind of modern parlance, this is a line operator which carries charge n under the U1 magnetic one-form symmetry. This theory. And I want to add in some left-handed Weyl fermions without loss of generality. Any right-hander I can just conjugate to a left-handed field. N left-handed Weyl fermions, complex Weyl fermions, with charges QA under this U1 gauge symmetry, and I want to scatter them off the monopole. And I want to work at tree level in E-squared. I want to consider neglect gauge field fluctuations. So I should be able to do this. Of course, if I now include gauge loops on top of this picture, it will change the physics, but I should still be able to work iteratively in E-squared. And so in particular, working at tree level in E-squared, I just have free fermions scattering off a background monopole. In other words, I treat this magnetic monopole as turning on magnetic flux in some background U. And so now I want to explain why this problem and why the non-triviality of this problem can be all phrased in the language of two-dimensional boundary conformal field. I do everything here is really, I think, manifest. There's no magic here. What I'm doing is taking each of my Weyl fermions from spinor field and decomposing in angular momentum modes. I've picked out a point, so I've broken translational symmetry, but I did still have rotations around this point at the origin, and so I can certainly decompose into angular momentum. If you really care about these things, if I take a spinor field and I decompose them, these things are called spinor-monopole harmonics. Spinors because it's a spinor, and monopole because there's a monopole. And these are like sections of a particular bundle, non-trivially, or non-trivial bundle because of them. So each mode, and I'll say more about these modes, I can think of each of these angular momentum modes as a chiral fermion in the two-dimensional boundary conformal field theory, whose directions are time and the radial direction. So it's precisely a boundary conformal field theory because my origin, where my monopole is, becomes a boundary in the two-dimensional picture. So the idea, well, the thing you should have in mind here is that any different scattering I consider in this, in two-dimensional language corresponds to different boundary conditions, this boundary in 2 dimensions. Let me assume again, without loss of generality, that the monopole charge times the electric charge of one of my fermions is positive. Otherwise, just flip this image like this. And I can look at the spectrum of angular momentum, and it's interesting. And it's not what we used to when we do an S-curve decomposition of the field without a monopole. In particular, we have a lowest lying angular momentum, which is not at zero, but is actually at this combination of half nq minus 1. So in particular, if you have anything more than the minimal monopole or something charged with more than minimal charge, the lowest lying, i.e. S wave at all is actually a higher spin mode. The other thing to have in mind there is that the lowest lying angular momentum mode is not necessarily fermionic, in the sense that it may have integer or half integer spin. Everything above this lowest lying mode is boring, and boring for two reasons. Firstly, just by decomposing the gauge field in 4 dimensions, it becomes a potential in 2 dimensions, and this potential generates a centrifugal barrier. As to say that these modes never actually reach the boundary. These are not free fermions. They're subject to a spatially dependent potential, which tells you, again, working at 3 levels, that they never actually reach the boundary. The second thing is that they're paired, in the sense that for every left mover, I have a right mover. And these left movers and right movers, by construction, have the same charges under any kind of global symmetries in my problem. And in particular, this means that there is an obvious boundary condition, which preserves all the symmetries that I want to preserve, which is that I just send in one of my left movers, and what comes back is my right mover up to a phase. This phase is from the perspective of the 4-dimensional system, is really the VEV, or the VEV of the diamond degree of freedom in one. The lowest lying mode is the interesting, and it's interesting for 2 reasons. Firstly, this lowest lying mode is truly just a free fermion, doesn't experience a potential, it's just literally a 2-dimensional free fermion, chiral fermion. And secondly, it's unpaired. I just have a left mover, I have no right mover. And vice versa, if I flip the sign of this charge, then I just have a right mover and no left mover. So seemingly, there is no boundary condition here which preserves energy. Now, of course, if I only really have one fermion, this is a sick theory to start with. This is a theory of a single var fermion, the U1 gauge theory. That has a gauge anomaly, that's not a well-defined theory. Necessarily, I have at least 2 fermions here. And as you'll see, kind of the whole point is that anomaly cancellation in 4 dimensions implies that there's always a solution to the scattering problem. All this to say, I'm going to throw away all of these higher modes. Everything above this S wave, which isn't really an S wave, I'm going to throw away. I'm just going to say I've got easy boundary conditions for these modes. And I just want to study, take all of my fermions, my N fermions, work out all of their lowest lying modes, and just look at the 2-dimensional boundary conformal field theory of those free fermions. The basic idea now is that the boundary conditions that I should impose on these free fermions in 2 dimensions are constrained by the symmetries of the problem. What are the symmetries? From my 2-dimensional perspective, what symmetries can I preserve by my boundary? The first thing to understand is that in this 2-dimensional free fermion theory, if there is some symmetry which has a non-vanishing Toft anomaly, I certainly cannot preserve it with my boundary condition. Why is this the case? I think there's two ways to think about this. I think that the cleanest is that the presence of this Toft anomaly is precisely the same as there exists a Schwinger term in the current OPE. So in particular, if I say a boundary condition preserves my symmetry, this is the statement that there is no flux of current through the boundary. If I assume that, then if I bring 2 currents together, I certainly won't find a Schwinger term. So there's another way to think about it. I'll say a bit more about this later, but we should think about being able to put a boundary in as the same as flowing to a symmetrically gapped phase, or symmetrically flowing to a gapped phase. And we certainly can't do that when there's a Toft anomaly, because you need something to soak up the anomaly in the half space. I'll say a lot more about that later. The kind of folklore, and I think most of the actual evidence for this comes from the symmetric mass generation picture, is that the converse is true. If I have a symmetry in this 2-dimensional free fermion theory that is non-anomalous, and it does not have a Toft anomaly, then I can write down some boundary condition which preserves the symmetry. And this is the assumption that I'll continue with. The key takeaway here is that what I need to do in my particular theory that I'm studying is work out all of these symmetries in 2 dimensions which have a non-vanishing Toft anomaly and use them to constrain my boundary condition. So what are these symmetries? We can be very systematic. We don't need to specialize to a theory. We can really get this on the nose. In 4 dimensions, I have the following vanishing anomalies. I certainly have a vanishing gauge anomaly. This is I'm just an abelian theory. This is a cubic anomaly with 3 gauge nodes. And that certainly is 0 for this to be a good theory. I'm also going to assume that I have my mixed gauge gravitational anomaly vanishes. I don't need to do this, but I am going to do this. And certainly this is true in standard model. And so I can take those conditions and ask what are my symmetries of my two-dimensional theory with vanishing anomalies. First thing is that the two-dimensional theory preserves energy. The gravitational anomaly in 2 dimensions, i.e. the difference of the left and right moving central charges, it's quite easy to see this is just proportional to this gauge gravitational anomaly in 4 dimensions, which vanishes. And so my boundary should be able to preserve energy. Similarly, angular momentum, my rotational symmetry, which is the space-time symmetry in 4 dimensions, becomes a global symmetry in 2 dimensions. And similarly, its anomaly is really the difference of this gauge and gauge gravitational anomalies, which by assumption vanishes. Also, this U1, which becomes again a global symmetry of this 2-dimensional theory. Its 2-dimensional top anomaly is just proportional to the 3-dimensional gauge anomaly. And more generally, if I have some global symmetry H, what I need is that this particular triangle diagram in 4 dimensions vanishes. This is a triangle anomaly with 1 gauge node and 2 global nodes. Again, for people who know a lot about these things, the precise statement, the idea that this triangle with 1 gauge node and 2 global nodes vanishes is just a statement that this symmetry in 4 dimensions does not participate in a 2 group with the U1 magnetic one-fold symmetry. This is the characterization, the kind of very pithy characterization of which symmetries I can expect to preserve. But you don't really need to know what all the words in this last line mean. So this is, believe it or not, everything here, although Callum never ever worded it in these ways, this is stuff that was kind of known. I worked very hard at this point to get kind of this 2-dimensional chiral conformal field theory, which some non-anomalous symmetries. And so what I should do now is just write down some boundary condition that preserves these symmetries.
At this point, why do you say it's chiral?
Good. So I've got the same number of left movers and right movers, but they're chiral in the sense that the symmetries I want to preserve act in a chiral way. That's what I mean by chiral. The problem and the 40-year roadblock on this problem is actually writing down these boundary conditions. There's a particular model that people who study these kind of things really love, sometimes called the 3450 model, which is extremely simple to state. This is a slight tweak on a 3450 model, but this is what I'll discuss. This is, again, 2-dimensional free fermions, 2 left movers and 2 right movers, and they have the following charges under a U1 squared global symmetry. Under one U1, they have charges 3450, hence the 3450 model, and under the other U1, I have 2121.
So can I ask you a more conceptual question?
Yes.
So you're interested in 4-dimensional scattering of these fermions, which is monopole. Like from asymptotics, like I should only, like for an S matrix, I should only be concerned about like asymptotic stuff, like asymptotic information. So why do I need to set something up kind of in the bulk of this space-time scattering thing?
Sure. So
is this an option? Is this just like, are you trading some?
I'll say more about the asymptotic states in a minute. I think the point is I create my asymptotic state. I have some asymptotic Fock space. I send something in.
But it cannot be single particle states, right? Because, I mean, that's there's this paper by like Turning and like Tellem and stuff that analyzed this, that you cannot, if you have magnetic and electric charges scattering of one another, you cannot treat it as single particle.
So it's pairwise felicity.
Yeah.
So this is consistent with this pairwise felicity picture.
I'm just trying to square these 2 pictures somehow.
Yeah, so the statement that there exists pairwise felicity in this picture is precisely the statement that the angular momentum spectrum is chiral. So one chirality goes down, the other one goes up. You start with 40 magnetic charge, you have paired angular momentum modes.
Yeah.
Precisely the statement that the system has some these guys call pairwise felicity.
Yeah.
Is a statement that your ingoers go half down in their angular momentum, and the right propellers go up.
But in
So
their
it's
setup,
like-
they never had to say anything about the boundary conditions on the monopole side.
No, they didn't. So what they did,
But like somehow this information, you must be able to trade information on this, like from this 2D side to some like asymptotic side. You know?
yeah, so what you can do, I mean, another way of saying this is one thing that we could have done, so I'll say a bit more about how to interpret.
If you do it later, then like
Yeah, but I'll say quickly now. The punchline of this will be, we'll know in the two-dimensional picture what the outgoing state is, and then we'll lift back to 4 dimensions. What one could do in principle is forget about the two-dimensional picture, have this ingoing state and just look in your spectrum for an outgoing state, find that it doesn't exist and you need something more exotic. Now, we could have done, but we chose to do it via the two-dimensional magical formal field theory. What those guys did was, morally speaking, to skip out the middleman and just work in the asymptotic Fock space and show that you needed something more exotic, which were these pairwise charged states. So there's no actual tension.
No, it didn't mean to imply that there's a tension.
Yeah,
I
yeah.
just wanted to like square these two.
Yeah, I think the statement is that there's no need to. So I'll say a bit more, but there are fortuitous circumstances where the scattering problem is uniquely solved. That is to say, give me an ingoing asymptotic Fock space state, and there is, at least within the class of states I'll discuss, a unique outgoing scattering state. And in which case, what those guys did and what we did give you, morally speaking, the same answer. What is more interesting, what will be very relevant for the standard model, are situations in which the symmetry is not strong enough to completely constrain the scattering. In which case, you're kind of at sea in the pairwise helicity picture. You don't really have enough control to say anything about what comes out. In contrast, here you have a classification, again in fortuitous circumstances, of Cardy states which preserve the symmetries you want to preserve, and so you have more of a handle on which part of the outgoing asymptotic Fock space you can access by scattering off this monopole. So these are the situations in which this gives you more of a handle. I'll say more about that. Yes.
Okay.
Thank you. Anyway, so this is this two-dimensional Fermion problem. Well, more or less everything conceptual in this two-dimensional picture we want to understand can be understood in this simple toy model. This has a vanishing gravitational anomaly, so energy is conserved. Also, my global anomalies vanish, thanks to Pythagoras. And so we should be able to preserve both energy and charge. Should be able to scatter something in, for instance, create a state by acting on the vacuum with this Fermion operator psi1. It's the left mover, it goes into the boundary, I should wait, and then I should wait some time and see what comes out. And it's not obvious what comes out. In particular, what Callan's half is precisely the statement that what should come out is 3/5 of psi1 twiddle and 4/5 of psi2 twiddle. Precisely because I sent in something with charge 3 under my first E1, and everything coming out has charge 5 or 0. So this is the only reasonable solution that preserves charge. And this equation, of course, makes no sense in precisely the way in which Callan's equation made no sense. So it's understanding what this guy is for this toy model, which will give us everything we need to tackle the more generic case. Cool, so let me tell you the solution of this problem. I, again, don't need to go via this step. I don't really need to think about bosonization, but I think it's the most useful way to think about this. Because in 2 dimensions, I can always replace modulo some discrete issues, replace free fermions with compact bosons. And in particular, in the language of these compact bosons, my properly normalized vertex operator gets scattered into an improperly quantized vertex operator. The nice thing is we really understand in the language of compact bosons what this operator is. The point is that if I take the 2-point function of some properly normalized right mover with this improperly normalized right mover, this 2-point function has branch codes. In particular, this is what people call a twist operator. And whenever we insert it into a correlation function, we need to attach it at the end of a topological line. This is nicer with pictures. If I have some insertion, some properly normalized insertion, which I can truly think of as a local operator, and I have this twist operator, it's attached at the end of this line in such a way that as I move this proper operator around, I pick up a phase. This phase is determined by this 3/5 here. And so this is why I have to attach it at the end of the line. This particular topological line, you can, it's a one-line thing to work out that this line implements a particular rotation in my U1 square, my global symmetry. And this is a generic thing. My non-anomalous global symmetry was these twist lines always live in that non-anomalous symmetry. In general, if I scatter a problem, this 3450 model, a properly quantized operator, i.e. with N1, N2 integer, I don't generate just any old line. I don't explore every possible twisted sector. I explore one of 5 twisted sectors. Either I don't get a line attachment at all, and my outgoing state can be expressed in terms of local fermions, or I have to put it at the end of this line L, or L squared, or L cubed, or L to the 4. It's quite a cute thing, and you can again now think about scattering twist operators, left moving twist operators, and see which twist operators come out right moving. And perhaps not surprisingly, you can never explore if you choose once you choose the twisted sector of your ingoing state. There's a finite set of outgoing twisted sectors that you can explore. So this is how we understand it in terms of compact bosons in 2 dimensions. I think it's more useful or kind of essential that we understand back in the language of free fermions. This is the picture we should have in mind. At some early time, I create some state by acting with some local free fermion, and then I wait. I ask, what state is my theory in at late? At late times, state that my theory is not created by a local operator, but it's created by a topological line which ends, and at this endpoint, I can address it with further local operators. I should stress that we really know what this operator is. This L is just a smeared fermion bilinear. It's just the integral of a fermion bilinear over a line. This is not something so crazy to say. I know how to write down this operator. If I want to work in canonical quantization, I can do this. I can write down what this operator is, and in particular its extent. But precisely because this line is topological, all of the energy and charge lives at the end. Furthermore, because this operator says, well, this line by construction admits a topological junction with the boundary, and therefore where it meets the boundary it also doesn't carry any charge or energy. So for the purpose of actually measuring charge and energy, this acts like a local operator. All the charge and energy is localized to this teal dot at the end. The actual local description of my theory is not created by a local operator. And so how do I actually, in this fermionic language, understand what the charge and energy of this endpoint is? I can just use the operator state map. My operators that can live at the end of this line correspond to states now in a twisted Hilbert space. Because if I do this operator state map, my line now becomes this line up my cylinder, which implements some twisted boundary.
Yeah, statement that the junction is topological assumption, right? That you don't have low-lying excitations on the
Yeah. Yeah, so the same as it's yeah, if you did have localized degrees of freedom, then that would it basically comes from that.
There's only one of the ways you could get that is if you actually had an non-trivial
Get what, sorry?
non-trivial degrees of freedom on the boundary.
Yes. Obviously, you don't have that. That would be one way to go. Yeah, I think the most concrete way to actually, I mean, the actual top-down, I guess, situation in which you really do have localized, normalized or further zero mode is in a supersymmetric setting, which then you would do, sure. So using this operator state map, I can now study and completely solve for the spectrum. This is a simple thing to do. And in particular, I can now look at the structure of this Hilbert space. It has a Fock space structure. Any operator that lives at the end of this line can be decomposed into a particular vacuum, this twist vacuum, which generically carries both energy and charge. And then I just have to raise, my raising operators are just my local fermions of my original theory. And so my scattering that I showed you on the previous slide, where I started with a psi1, becomes precisely this scattering. This is the solution to that scattering problem. That I take my outgoing state, which has the correct charge and energy, is my twist vacuum with two creation operators. And so now we kind of know the rules of the game. Rules of the game is that I tell you what my ingoing state is. I need to look for an outgoing state which has the correct energy and change. And a thing that is, again, essentially linear algebra is that if the amount of symmetry, I need to look at the symmetry that I can preserve or constrain my scattering with, which will have a particular rank. If that rank is at least as big as my left and right moving central charges, then my scattering problem is completely fixed. There is a unique twist line, a unique twist operator, which solves the scattering. Again, this is easiest to see in this Bose-Nice picture where it really is just a linear algebra problem. So now I've entered 2D land for a long time now, and I need to start thinking back in terms of 4 dimensions. Once again, this is my picture in 2 dimensions. This is the picture we propose in 4 dimensions. That in my 4-dimensional picture where I lift back up, what I should do.
Okay, before you go on, like what exactly does it mean the scattering is completely fixed? The S matrix is just like there's one S matrix element, like you know exactly the in state, you know the outs. There's a single out state that you can generate. But this is like some leading order thing, like because why can I not have pair creation?
Sure. This is all tree level. This is tree level scattering off this heavy monopole. And the statement is that in the outgoing Fock space, so my asymptotic outgoing Fock space is local operators plus all of these possible twist operators. And the statement is within that entire extended Fock space, there's precisely one state which has the same energy and charge as the ingoing state. Is this controversial?
I mean, I don't know why you cannot radiate off like the outgoing charge. It's charged fermion, right? Mm-hmm. Oh, but they have weird charges. Why can I not just generate another E plus E minus pair? Because the charge does not work out, I guess.
Yeah.
Okay.
I mean, sure you can do that,
but then there's a difference, right? Whether I have like 3 outgoing electrons. That's the energy versus
everything you're describing is beyond tree level, though, right? This is
no, that's a tree level process. I mean, I don't know what you mean tree level, like, or this is like, are you saying E squared? It's a beyond E squared process, but it's still tree level.
Sure. Okay. It's a perturbative correction on top of this picture. Yeah. It's still tree level. So yeah, I guess I'm using tree level incorrectly, but it is still a perturbative correction on top of this leading order picture.
Yes.
Sorry, no, it should be much worse than that because you're imagining that the E plus or minus pair is neutral under all symmetry. But that's not actually true. The left moving and the right moving electron get shifted.
I'm not talking about left. I'm not talking about a 2D picture now. I really mean like 4D. We're doing 4D, right? Like I scatter in some electron on this monopole, out comes the electron, so I can have in principle photon branch problem, and then the photon splits into E plus E minus pair. Why can I not have one?
It's photon.
Oh, sorry, there's no photon.
There's no photon. No, this is free from. So
okay. You have no.
I mean, yeah, what you're describing is a perturbative excitation of the gauge on this background.
Without the photon, even in free fermion land, I thought that this would have been one of these massive modes that you discarded, the massive left right.
But if you have a free then you cannot have the splitting process that I was describing.
But this question of whether even kinematically there's a state with more fermions in the Fock space that would conceivably be an out state. I think you're saying that even that's not true.
No, yeah, because true. In any little local ball, you've got to preserve angular momentum, so necessarily you're going to be into this paired part of the spectrum, not an axis spectrum.
So as long as you scatter kind of below the gap to that,
Yeah, I mean, if you give me a phase shift, right?
The phase shift.
Well, we're going to come out, but then there's some additional, yeah, there's a phase shift.
There is a phase shift, yeah.
That's computable.
So the phase shift corresponds to the value of the dial degree of freedom of the, so when you specify your top line by our description of this topological monopole, you also have to specify the value of the U1 value dial degree of freedom. So you can't excite it though, by assumption that it's capped. So it's capped, right, it's capped. But it's kind of input to the problem, I suppose.
What is this from the point of view of the boundary? Angle?
It's just a phase shift in the wave function.
And it's completely arbitrary, it's not fixed by any art condition.
No, it's not. Yeah, so it's so this is the picture we kind of propose in 4 dimensions. Picture is that as you look, I have an ingoing state, which if I want to work in this lowest lying angular momentum mode, you can think of as being created on the 2-sphere and it moves in. And at late times, the state that my system is in is not created by any operator which is localized to a 2-sphere. It's instead created by an operator as supported on a 3-ball, which center of which is my top line. But by my 2-dimensional computation, all of the charge and energy carried by this configuration lives on the surface of this ball. I should say as well, in all of these problems, there is an equivalent local description of this entire system in which the ingoing state is created by a ball and the outgoing state is created by a shell. This is the sense in which these 2 excitations are mutually non-local in precisely the pairwise helicity sense. So there's no single local description of this theory in which both of these excitations are just created by an operator living on a shell. But it's only that one excitation is non-local with respect to the other. This is the 2-dimensional analog of the statement that I only detect this line by moving one operator around it. So this kind of sets up my recipe, what I need to do to solve these kinds of scattering problems.
Yeah, maybe you'll mention something about it. So far, you've treated electric charges at global 0 form symmetry.
Yes.
And therefore you have a topological surface.
Mm-hmm.
But that changes once you gauge.
No, so sorry. We'll see in some of the model, the topological surface is a surface for a 4-dimensional global symmetry. It's not the gauge.
But in this toy model, it was.
No. In this toy model, sorry.
I thought electric charge was one of your U1 symmetry.
It was, but I didn't tell you where the topological surface. So in this 3450 model, for instance, the 3450 model actually doesn't descend from a 4-dimensional description. That's just a 2-dimensional model. So generically speaking, the surface actually it'll live both in the gauge group and the global symmetries generically. And there is one monopole that we know how to solve in the standard model where we'll see an example later, but I don't know of an example where the 4-dimensional surface necessarily is pure gauge. But
even if it's partially gauged, then.
But still, I think what we're saying here is that if you have a topological surface in 4 dimensions, which generates a gauge symmetry, and you cut it open, the M still carries charge. It's essentially a Gukov-Witten operator. Now you don't see the surface because it's pure gauge. So you really now, in the gauge theory, this operator now is really supported on the 2-sphere. But its endpoint, that this operator, which is a Gukov-Witten surface, it carries energy and charge. So that is the correct thing to say. And so generically, what you find is that this codimension 1 surface in 4 dimensions acts both as in the global symmetry and the gauge symmetry. And when you go to the full gauge theory, it is a cut open 3-ball global topological operator, rests on its boundary with a particular Gukov-Witten surface.
But the reason it'll never be pure gauge because otherwise it would actually be.
So there is an example in the standard model where there are 2 options for what this 4-dimensional surface That's this co-dimensional one surface and four dimensions. And one of those two options actually is pure gauge, and there doesn't seem any a priori reason why it can't be the solution to the scattering. There's nothing. I think the statement is if you want to work in an approximation which you treat your gauge symmetry as global, then necessarily this thing is non-local, but in the full gauge theory, it can be a local operator. I don't think there's a tension there. It's just in taking your IR effective description to treat your gauge symmetry as a global symmetry, in making that step, things which were local in the gauge theory become non-local in this IR effective description.
But in that case, like, maybe you'll get to it, sorry.
Oh, no.
I'm just saying in that case, would you avoid any strange fractional?
No.
No.
No. Because you have this Kukov-Witten operator still, which will carry fractional charges under any, generically under any symmetry in 4 dimensions, which has an ABJ anomaly, will become fractionalized. So we'll see in the standard model, in that case, baryon electron number is still fractionalized, even though it's a local operator.
And when you say
well, not local,
operator, you mean for the magnetics?
It's local in the 2-dimensional sense. It's still smeared over a 2-sphere in the 4-dimensional sense.
That's fine, but it didn't have anything in the interior.
Yeah. So this is my kind of recipe for success, the steps I need to take in order to solve these kinds of scattering problems. First, I determine the symmetries which are preserved by the monopole, which we said corresponds to how the interplay of this magnetic one-form symmetry with my other symmetries. I then need to determine the 2-dimensional chiral boundary conformal field theory of these lowest lying angular momentum modes. In particular, the charges of my fields in 4 dimensions will tell me how my 2-dimensional modes are charged under the SU2 rotation global symmetry in 2 dimensions. And then I will constrain and hopefully return scenarios solve my 2-dimensional scattering. And we've seen that the scattering will generically generate a topological line. I then, at my 4th step, and the step which is kind of the most ad hoc, is determine a 4-dimensional zero-form topological surface, which reduces in 2 dimensions to that topological line. And then I come here and tell you about it. So let me now talk specifically about the standard model. If you're anything like me, you spent years in the superconformal wilderness and you needed reminding what the standard model was. This is the standard model I'm going to describe. There's not one standard model, there are 4 standard models. They all have the same local form of their gauge group, SU3 cross SU2 cross U1. But you have a choice of discrete quotient. There's a Z6, which doesn't depend on any of my fermion fields. And so by looking at local physics, at least, there's no way of telling what that quotient is. What it tells you is what the spectrum of Toft and Wilson lines is in your theory. I'm going to pick the maximal quotient, the Z6 quotient. I could pick Z3, I could pick Z2, I could pick nothing. The maximal choice gives me the maximum number of Toft lines and the minimal number of Wilson lines. I should say that most, not all, but most guts give you this maximal quotient. And we'll see that the Toft lines which remain, if I think about the minimal quotient, none of them are actually solvable using these, completely solvable using these methods. So this is why I took this maximal quotient. This is my matter content. I have some left movers and some right movers with the following charges under my various. And I have a single global symmetry, which has a non-zero or a 0 ABJ anomaly, which is B minus S, baryon number minus lepton number. I should say as well that there is also a single U1 symmetry whose ABJ anomaly is only abelian, i.e. its only ABJ anomaly is with U1 hypercharge. And one thing that we now understand is that you can always salvage some discrete rotation in this U1 symmetry as a non-invertible symmetry. This particular non-invertible won't actually play a role for the monopole I'll solve, but I'll say more about its relevance later. So now I want to talk about what regime I want to actually study. And so I have a gut scale. I don't care about what my gut is. All I care about is that this gut gives rise to the Z6 quotient. So in particular, the SU5 gut gives us many guts will give this. I'm going to be agnostic. And the whole point of this whole program is that I'm agnostic about the actual nature of the degrees of freedom living within my monopole. What I care about is that my IR description is valid. If I'm scattering at too high energies, then I really do probe these internal degrees of freedom. I really need to solve a problem with a truly dynamical monopole, which is this tough particle monopole in this non-abelian gauge theory. So I don't want to do that. If I go to very low energies below the electroweak scale, then the fermions I want to scatter are massive, and my description doesn't apply. This is a vector-like theory now, and the scattering is easy. I want to study this intermediate regime in which I'm much lower than the gut scale, so my monopoles are very heavy. I can treat them as tough lines in my gauge group. But I still have these massive fermions, which weren't Higgs by this symmetry breaking. They would have been by this one, but I'm much above the electroweak scale, so I can treat them as massive. Also, for that same reason, I can neglect gauge field fluctuations and treat this standard model gauge group as a global symmetry. In other words, work at leading order in the gauge coupling. So I need to actually think about what tough lines my theory has, and this is really the most kind of bookkeeping slide. There's nothing super deep about this, but there is a GNO classification of GNO-like classification of tough lines in this theory. In particular, spherically symmetric Dirac monopoles take the following form. So I have 4 integers I have to pick. Basically, it tells me how this monopole winds within my gauge group. I should say that there's a much coarser characterization of these, which is in terms of the magnetic one-form symmetry. There's a U1 magnetic one-form symmetry, which is just the fundamental group of my gauge group. In particular, under this U1 magnetic one-form symmetry, these monopoles have the following charge. So there's many, many GNO monopoles which all have the same topological charge. I should say, in the actual full gauge theory, where I do include gauge field fluctuations, most of these monopoles are unstable. Okay, most of them are actually screens. What we showed is that unless all of these integers are very small, i.e. at most 1, these monopoles are unstable to W boson condensation. There are off-diagonal W bosons that get sucked in and screen the magnetic charge. What you actually find is that for each value of this topological charge P, there is precisely 1 stable monopole. This is a very generic result. But do ask me about this, I have a backup slide to tell you more about. My generic monopole will break the non-abelian bits in my gauge group, but I will nonetheless always have some rank 4 subgroup which is preserved, and that 4 is the only number I care about. Energy is also preserved, again, by the vanishing of the anomalies in 4 dimensions. SU2 rotation is preserved, and B minus L is also preserved. So I have a rank 7 in total group that is preserved. And so all I need to do is look at all my top lines, decompose their spectrum of fermions, and ask how many low-lying modes do I have? How many chiral modes do I actually find? And I need to look at the monopoles for which I have at most 7 left movers and 7 right movers. Generically, I'll have many, many more than that. But you can just look at this GNO classification and find the ones which have few enough fermions in this S wave. It turns out there's 9. Okay, it's just, there are 4 of them which have yes, 4 ingots and 4 outgoers, and there's a further 4 which have 6 and 6. So let me talk about the kind of minimal monopole, the one of lowest topological charge, the kind of simplest non-trivial situation. This is its field strength, and so let's really get our hands dirty and see what we do. What I do is I take this left-handed electron, which is in the 2 of my SU2 weak. I look at each of its 2 components. I see what kind of magnetic flux it fields. I just see, based on its electric charge, what magnetic charge it experiences. In particular, this top component doesn't see the monopole at all. Okay, it just doesn't see it. The bottom component sees magnetic charge -1, and so in particular gives rise to a single right-moving mode of my 2-dimensional solution. So I can just do the hard work and go through all these modes and ask, of these 15 fermionic fields in the standard model, which ones actually give rise to chiral modes. And in this particular monopole, I get 4 left movers and 4 right movers, which, if you really care, are these particular components of my 4-dimensional Weyl fermions. So that's nice, and they're all spinless. They all have vanishing spin under SU2 rotation. So in particular, all the symmetries in my 2-dimensional model, which are on a preserver abelian, and that'll be important. And so I can now solve, and this is the monopole that Callum was really studying. I can solve for the scattering, and what I find is that for a generic, properly normalized ingoing state, the thing that comes out is either just a local fermion that's boring, or in cases like that right-handed electron that Callum considered, lives at the end of a particular twist line. The endpoint of this twist line gives rise to a twist vacuum. There's actually a little quirk of this particular situation because it's Z2. Specifically in the case of Z2, these are Ramond boundary conditions. And so you have a twofold degeneracy of this twist vacuum. There's nothing super deep there. You can distinguish them by different charges. They carry different global charges. There's actually a twofold degeneracy in this twist vacuum. So this is the equation that Callum wrote down. And this is the solution to the scattering problem in the language here. So this right-handed electron scatters into an operator, which is a twist operator dressed with a single left-handed electron. Now, this is a nice equation in a formal sense. I can understand exactly what the state is in my Fox test. What does it actually mean? What does it mean in terms of things I can actually measure? Note that this twist vacuum carries baryon number and electron number minus half. Baryon number should be quantized in third integers in this normalization, standard normalization. Electron number should be quantized in integer. In other words, this twist vacuum fractionalizes these. Now, of course, both baryon number and lepton number are not good symmetries in the sense that they have ABJ anomalies. So they're not preserved by scattering. But nonetheless, by scattering that doesn't involve monopoles, they're not fractional ones. If you've got some instanton process which will change this baryon number or lepton number, it will only shift them by baryon number by third integers and lepton number by integers. This is an extra process. This is something more interesting, which actually fractionalizes these symmetries. This is the smoke and gun of this kind of scattering. You can show that when you have this kind of scattering into these twist operators, there necessarily exists some ABJ anomalous symmetry which becomes fractionalized. It's that symmetry that that charge you should measure to understand whether or not you really have generated something weird. And so now I know for this minimal monopole how this line acts on my two-dimensional chiral modes. All I need to do is seek some surface in 4 dimensions which reduces to this line in 2 dimensions. So again, for this minimal monopole, it turns out to be 2 viable options. And as I was saying earlier, what is interesting, I should say that this is just a statement that remember, I had 15 fermions in the standard model, but only 8 of them give rise to chiral modes. And so, in particular, there is a Z2 symmetry subgroup of this, which only acts on the modes which don't give you chiral modes. That makes sense. There's always, for this minimal monopole, a Z2 degeneracy in actually precisely saying what the outgoing state is. For these other solvable monopoles, there is not such an ambiguity there. You can really, on the nose, pick out what the operator is. But these are the 2. I should say, one thing, I think the only thing that can possibly single out which of these 2 options is correct is by actually studying fluctuations above this picture. So that was the solution to that particular scattering problem. But let me say some more things about things we still don't understand. Let me first summarize. The point of this talk was to study massless scattering of soft lines. At very short distances, these are really dynamical topological solvers. I have a UV description of this theory, I have a UV completion. This scattering must make sense. I think this is why this motivation for this problem in terms of a Higgs UV theory is really important, because this thing is completely smooth. Deep in its interior, there are some localized degrees of freedom. I send something in principle, this ingoing excitation interacts with all these ingoing or this UV degrees of freedom for a very, very short time period, excites them, but they all settle down, and then something comes out. There's nothing, this must make sense to scattering. And so this motivates us to actually understand what's going on in the ion. The puzzle was that in order to actually make sense of this in this description, we needed some form of exotic state. The mathematical lesson, I suppose, is that these states always existed in the theory. There was nothing we had to add extra. There was no breakdown of our description. It was just that we needed to consider a more general Fock space, asymptotic Fock space. Rather than just considering states created by operators living very far away, I needed to also consider operators living at the end of some ball which fills my space. The physics lesson is that these new states allow us to preserve all non-anomalous symmetries, while generically always fractionalizing some which do have anomalies. I guess the punchline or the kind of maximally punchy thing to say is that if there are magnetic monopoles, then we necessarily have exotic matter with these fractional shelters. I want to lastly just say a few words about when what I've said doesn't work, because I think these things are kind of interesting. I said this recipe, this is always fine, this is always fine. This fourth step, that of taking my two-dimensional line and finding some four-dimensional topological surface which reduces to the 2D line, is sometimes subtle. In particular, there are situations in which the only viable four-dimensional surface we know how to find is a four-dimensional non-invertible symmetry, which is fine. There's nothing a priori wrong with that. The simplest example is just n fermions in QED of a non-linearly charged monopole, monopole of charge not 1 or 2, but 3 or higher. All I'm finding, and I can tell you more about this, is that the topological operator is a axial rotation which has an ABJ. In particular, in the standard model, we do have one particular symmetry in 4 dimensions, which is invertible. One that just rotates the right-handed electron. And so we should expect that generic scattering in this standard model should also generate such non-invertible. So it's not purely academic observation, this is really physically relevant. Should say as well, this step also breaks down. I think this is even more interesting than this breaks down. Sometimes we can't even find a two-dimensional line which does the trick. When the symmetries you want to preserve are all abelian, this never happens. When the symmetries you want to preserve are abelian, there is always a solution. I'm talking maybe a bit more precise with that. I've got n fermions, and I've got some abelian symmetry I want to preserve. If that abelian symmetry is big, then I can actually solve the scattering uniquely. But say I've got n fermions, and I've got a rank 2 or rank 3 abelian group. I can't solve the scattering, but I can at least actually classify, or I can present and classify all possible outgoing states consistent with the symptoms. What goes wrong when we have some non-abelian symmetry? There's some non-abelian symmetry, such as SU2 rotation. Sometimes it is the case that my left movers and right movers have to carry different anality under this non-abelian symmetry. In other words, different charges under the center of my non-abelian. The twist lines that we've considered can never change the anality of the operators living. So in particular, again, this is not a purely academic observation. In the SU5 gut, the charged 3 monopole of the SU5 gut gives rise to one of these GNO monopoles in this IR description and standard model. And it's very easy to cook up an example. This example where the left movers, there are some ingoes which carry charge into the center of SU2 rotation, i.e. a fermionic with respect to SU2. But all outgoers have integer spin. And so nothing we can do in this whole setup can solve this. This is a problem. A problem not least because this is really physically relevant. Once you accept that we're considering magnetic monopoles in the standard model, then it's a very physically relevant situation. And we don't know how to solve this, but I can tell you some directions. Finding some other directions, we can consider gauge field fluctuations above this picture. We know a little bit about this in some simple examples. What generically happens is that some of my modes, which these lowest lying modes, which didn't have a centrifugal barrier, actually at the total level do generate a slight centrifugal barrier and get lifted in vector-like pairs. But there's index theorems which tell you that you should always get some minimal sets. So there are toy models we know where you can lift some pairs of fermions, left and right moving pairs, by considering such fluctuations. Another thing which I guess I've glossed over a lot here is we like to think, if we really want to make contact with particle physics, we really want to think about particle tracks. We want to think about creating some wave packet ingoing and some wave packet coming in. What I told you is really inconsistent. What I told you is I create some wave packet, I decompose it into angular momentum modes, and then the lowest lying mode does something wildly different to the higher modes. Is there something wrong with that? Maybe not, but it doesn't feel very natural. What is interesting is that these twist operators coupled all my higher angular momentum modes. So I know how to, at the edge of this topological ball, localize charge and energy. But that's not what the scattering solution is telling me to do. At least at this leading order, what it's telling me to do is do that for the lowest lying mode, and for the other modes, don't. Is there a tension there? Maybe there isn't. Maybe it's just an artifact of working in this leading order approximation. But nonetheless, it's something that confuses us. Finally, these remaining scattering puzzles. What are the possible resolutions? I think that the most conservative, there are kind of these monopoles that we can't solve for. I think there are 3 possible resolutions in increasing level of drastic. The first, I think, is possibly the most likely, which is that we just need to consider something even more exotic. There's some fancier 2D twist operators that we need to consider. There's something we've missed. The kind of slightly more adventurous option is that the assumption of an internal gap breaks down. Precisely, this is a very, very, very indirect way of seeing that for these Plichter monopoles, they're actually exactly gapless modes living on them, even when there's no supersymmetry or anything else protecting those modes. As I think, so quite a bold proposal, but it could be true. The third is also kind of quite bold, which is the statement that actually I talked about how this UV description must exist and therefore scattering must make sense, but it could be the case this UV, in this case, there's something very strange that happens at high energies that we can't probe, actually breaks the symmetry. This doesn't seem consistent in the standard model picture. It would be an extremely bold statement about the UV behavior of the standard model, or of guts. But is it?
But that would certainly be true for this non-invertible symmetry.
That would certainly be true. Why?
Non-invertible symmetry is only a symmetry because you have an emergent magnetic one-to-one symmetry at low energies.
True.
At the gut scale, that's just badly broken.
But I've not imposed that any good. So the symmetry that in the standard model that this rank 7 symmetry that I've used to constrain my scattering, everything was inverted. It may be the case that I generate some twists at some topological surface, which is non-invertible. What I'm talking about here, the assumption that went into this is that my scattering can preserve this symmetry. That symmetry that I'm trying to preserve was all invertible. It was the gauge group times B minus L times energy times angular momentum. Everything was invertible. I agree with you. So it turns out that actually that scattering that I showed you, so that the scattering solution for that that minimal monopole breaks the non-invertible U1 symmetry in the sum. It doesn't preserve that symmetry. So that symmetry rotates the right-handed electron, but doesn't rotate anything else. So in particular, that scattering doesn't preserve that symmetry. So it's not that I didn't, it's more than just I didn't use it to constrain it, it actually manifestly breaks it. But I agree with you, if I had used it, then there would be a contradiction. Well, in a way, actually.
But this is much more satisfying. You would expect the monopole to break the symmetry. Right.
Yeah, it would be satisfying if the ones for which we couldn't solve the scattering were precisely the ones in which we'd use the symmetry to constrain the scattering that we weren't allowed to use. But that sadly isn't the case.
So you're saying there, the examples you're worried about are when we only use gauge plus B minus L.
Really, we need angular momentum. Angular momentum, you have
Even just like.
yeah, even just angular momentum. You have Ingo mode, or there's actually an even simpler model. It's the 15789 model. You have left movers and right, or you have, yeah, you can cook up just simple examples of four-dimensional abelian gauge theories, which give rise to a spectrum of lowest-lying chiral modes, such that only the ingoers are charged into the center of SU2 rotation, and none of the outgoers are. And then we don't know how to. So any twist vacuum, so a non-degenerate twist vacuum is trivially doesn't carry any charge under SU2 rotation. If you have a degenerate vacuum, you can, but you can show that if the outgoers are not charged, if the outgoers have a particular anality, you can't change the anality by considering such a degenerate vacuum. I can show you yeah, there's got to be something new. I don't know what it is. I have some other backup slides on what new things it could do. I'll stop for now.
Can you say a little bit more about why in the non-abelian case, when the analogies are different, there's no surface? What?
I think it's quite simple. I think the idea is that so say it really is just SU2 and you have some left movers, some right movers, and these guys are charged under the center and these guys aren't. And then you try to build some twist line. First thing to say, so the Fock space that you build here, it has the following structure: the twist vacuum plus whatever right moving fermions you had. These right moving fermions, by assumption, do not carry any charge under the center of SU2. The only way out is if a twist vacuum itself carries charge under SU2, the center of SU2. Now, if the twist vacuum is unique, then it's uncharged under all non-abelian symmetries, and therefore necessarily doesn't add charge under the center of SU2. The only way out is if you have a degenerate twist vacuum. You have a degenerate twist vacuum in precisely this situation. So your twist line acts on your right moving fermions as phase. If all of these rotations are not by pi, then you have a trivial vacuum. If some of them are by pi, i.e. some of them square to 1, you actually have Ramond boundary conditions for some of your fermions. Whenever you have Ramond boundary conditions for a free fermion on a circle, you get 2-fold degeneracy. So generically speaking, you have a 2 to the n degeneracy here, where n can be anything between 0 and big N, depending on how this twist acts. So you think, okay, now I'm in action. Now I actually have this degeneracy of twist vacuum, and in particular, these carry a non-trivial representation of SU2. But the problem is, if these have SU2 representations R1, Rn, all of these states in the twist vacuum only live in the possible tensor products of these representations. So some tensor product of R1, some subset of these, all of the representations of SU2 which you can explore by moving around in the space of twist vacuum. In particular, if all of these representations, by assumption, are not charged under the center of SU2, then none of their tensor products are either. So that's kind of the simple proof that these kinds of twist lines can never add anality if you didn't start with it. Of course, if you had SU3 and then you've got anality 0, 1, or 2, as soon as you have 1, then you can do tensor products to get anality 2, etc. But if you start with anality 0, there's no chance of getting anything other than anality 0 with these kinds of twist lines. So we do this, but we thought maybe it's not, maybe there's some way of showing that this doesn't happen until we realized that for a very simple monopole in the standard model, it does happen. Which was both, slightly surprising, because we kind of assumed that certainly for generic monopole and standard model, you've got too many fermions to actually solve uniquely this scattering. You still hope that you can write down and there is some possible outgoing state. But there are these very simple monopoles in the standard model for which we don't even know anything you can write down. No any outgoing state which preserves angular momentum.
You're saying you don't even have to know anything about the boundary condition. It's just a question of whether this line exists.
Yes.
It's a question of the bulk theory.
Yeah. Well, you need to know that the line can end somewhere in order to generate it. If you
Well, that's an additional question.
yeah.
It's a question of whether there's any line.
Yeah.
That's equivalent to saying there's no Tuft anomaly in the 4D. They're more.
So the fact that it can end, so you need a vanishing Tuft anomaly. So the vanishing Tuft anomaly in 2 dimensions means so you need this line generates a symmetry which has a vanishing Tuft anomaly. Means that you can end it topologically on the boundary.
Well, it would be very interesting if there's some cases in which you can prove that it cannot end topologically.
What is in
That could happen.
yes, as in indirectly through this saying that the only way to solve the scattering is if
There's different levels of waffles. One is that not even the line exists.
Yeah.
But maybe there's a couple of logical lines, but it can't end topologically. Then the boundary would have to carry something that carries the transforms under the center of the
Yeah.
symmetry.
That would be interesting.
One is extra.
That would
Zero mode extra degree.
that would be very interesting. I didn't know you can play around almost to death with different toy models here, and it'd be very interesting to cook up a situation in which a line does exist, but this endpoint necessarily carries some charge.
But since you claim you have an example in the standard model that engineers this,
Yes.
you could ask whether this particular monopole has funny zero modes or something from the UV point of view.
Would it?
The gut, let's say from the gut point of view.
Funny zero modes.
I don't know, you could imagine that something funny happens.
Well, that would be the indirect conclusion. If you could argue that the only way out of this is if there is truly some normalizable Fermi zero mode for this monopole, then sure, the conclusion would be that for certain. But are you saying you want an independent way of seeing that you have these funny zero
Since
modes?
you might have, well, I don't know, we didn't quite understand whether you got a gut in which this monopole arises or,
Yes, SC5 guts. Just
but then in principle, you can study the zero modes of the
Yeah.
gut on the monopole.
you can.
So is there something odd?
I don't think. As far as I know, there is not, but maybe it's been missed. Yeah, I don't know. That would be a very neat way out of this.
It's like the chicken. Guess we didn't get to.
Do you have any secret backup?
I have some secret behind. I tell you, it will take about 2 minutes. So this is other ways of characterizing these extra value functions. So I guess one route to the way in which we constructed these boundary conditions was extremely ad hoc. We said, here are the symmetries which I want to preserve, and therefore look at my spectrum of lines and classify, determine the Hilbert space and look for states with the correct charges. It would be nice to actually have different ways of generating these boundary conditions, because then that gives you another thing you can try to generalize. So let me talk about 2 of these. So one of them is all about symmetric mass generation. So suppose I have on the extremely generic here, some UV theory with some tunable parameter. And for one value of this parameter, I flow in the IR to some trivially gapped theory. On the other hand, for some other value, I flow to n 3 direct forms. If I can do this all while preserving some symmetry, some necessarily non-anomalous symmetry, because I go to a trivially gapped phase, this is what we call symmetric mass generation. And so the idea is very simple now. I just do this tuning of this parameter in a spatially dependent way. I tune it to one value in x less than 0. So I start on the infinite line, and I gap the theory here, and I don't gap it here, and this should dynamically generate for me these boundary conditions. The fact that this is a symmetric path in theory space which preserves the symmetry, by construction will generate for me G preserving boundary conditions. But a very, very simple example that you can really do extremely manifestly is just a single Dirac fermion. Now you have two possible symmetries which have a vanishing anomaly. Either U1 vector or U1 axial, they have a mixed anomaly, each individually has a vanishing anomaly. And so this is now super obvious. I can get this UV theory in a simple way. I just turn on a mass term. To get the U1 vector preserving boundary conditions, I turn on a mass term side left, dagger, side right. And I just set my mass non-zero here and 0 here, close the IR. In fact, you can do this super concretely. You just solve the spectrum for the Dirac operator with this spatially-dependent mass term, and you see directly that the eigenstates in the IR have the boundary condition side left equals. If you put in a phase here as well, also if you want time reversal symmetry, this phase should be 0. But you manifestly generate this boundary condition. It's a very key thing.
There's absolutely no reason why the boundary condition should be gapped. This example, for example, is gapped. Get some Fermion zero mode stuff to them.
There's no reason why. So you're saying
it's a beautiful way of generating a boundary condition that preserves the symmetry, but generically it's gapped. The boundary.
Yes.
Which what you want, what you're doing, you don't want.
True. But one might hope that by fine-tuning how you actually do the symmetric mass generation, you can also ensure that the boundary is gapless. Sorry, gapped.
In this example, it's clearly not possible.
In this example, it is possible. So, you can do this calculation. It's really just solving for a generic profile or generic like Tanch profile for M, solving for the spectrum of the Dirac operator, and then just taking the Tanch very strong and looking at where you go. You end up with a spectrum, end up with no. So you're worried about
there's 0.
I don't think so, but let me double check. Again, maybe that depends on exactly what profile for M you pick. And you can ensure. I didn't think there was in this case.
Sorry?
I didn't think there was in this case a normalizable 0 mode.
You from positive end to negative end.
Yeah, so if you go from positive to negative, then you get a SPT,
Right, okay.
and then you have an E-sing line in the middle.
Right.
So yeah, I guess this is the point. So if you go from M very positive and very negative here, then you generate a theta angle of pi here and 0 here, and you necessarily have twofold degeneracy of vector here, and you get an E-sing line in the middle. Here we're going from 0 to very low. Yeah.
0 to positive.
Yeah.
That should be okay.
I think that's okay, but if you're going from positive to negative, you get a theta angle here, no theta angle here, as you well know, you get an E-sing line in between. But not in this case here. Should say as well, in this simple case, if you just put on a Myra or this kind of mass, then you end up with the other boundary condition, which preserves U1 axial. So what we know how to do is to do this kind of symmetric mass generation for generic symmetries of these M Dirac fermions. I can tell you exactly how to do that. The punchline there is whenever the symmetry is chiral, necessarily there's no mass term you can put on. You have to do something more complicated. What we don't know is from these methods of symmetric mass generation how to actually read off, if you like, these boundary conditions. How to actually determine. So for the 3450 model, for instance, I know how to symmetrically gap it. But I don't know how to read off from that symmetric mass generation procedure exactly what these boundary conditions are, which is the gap that still needs filling. The other route is kind of surely related, but also kind of key. Now I want to start with N just purely left-moving Weyl fermions, and I'm going to gauge some symmetry. Now, the only non-anomalous symmetries of N left-moving Weyl fermions are discrete. And so I can gauge some discrete. If I choose this gauging correctly, and it also comes with a choice of discrete torsion when I do this gauging, the theory gets mapped back to itself. The local description of the theory is exactly the same. But again, the cute thing to do is to just do this in a half space. This is half space gauging. And what you do is you generate some defect in the middle. In this case, is what we will call a Hambara-Yamagami defect. The point here is that now local operators, as I go through this defect here, pick up some topological line attachment, which looks an awful lot like my scattering picture. And indeed, from doing this, all you now need to do is fold the theory, and you get precisely the scattering picture. We understand how to do all of this for preserving these abelian symmetries in this language instead. What this tells you is that another way of characterizing these symmetry preserving boundary conditions is self-maps of this theory. Things I can do to this theory, such as discrete gauging, which send it back to itself, but possibly leaving the residue of some defect. What is nice is that we know exactly how to do this discrete half-space gauging and generate this non-invertible defect for all abelian symmetries, but we don't know what to do for non-abelian symmetries. Hopefully something that's an obvious, or obvious, but a generalization of that picture, but we're not quite sure what it is. Okay, now I actually am done.